The sharks in this video are biting at what they think is prey, but actually is an electrical field provided by 4 coils embedded in the seafloor. Sharks have a special ability to perceive the electric field produced by a prey or a potential mate, and this is called electroreception. All charged bodies are surrounded by an electric field that can apply electrical forces on other charged objects. Since electrical fields apply a force in a particular direction, they are vector quantities. The strength of an electrical field is the ratio of its force to the magnitude of the charge that receives that force. It has the units newtons per coulomb. The direction of an electrical field is drawn to show how the field acts on a positive charge. Since positive spherical charges push positive charges away from its center in all directions, the arrows point outward. Since a negative spherical charge pulls positive charges towards its center, when you draw the electrical field lines of a negative charge, the arrows point in that direction. If you have trouble remembering that the electrical field lines are drawn to show how the field acts on a positive charge, I have a neat little memory trick for you. The word out, O-U-T, ends in the letter T, so that looks like a positive symbol. The word in ends in the letter N, which should help you remember the word negative. There are 3 things you need to know about an electrical field around a spherical charge. That the positive charge has arrows that point out away from the center. The negative charge has arrows that point in towards the center, and the field inside the charge at the core of the charge is 0. Here's a little test for you. Can you identify the positive charge? The right charge is the positive charge because the arrows radiate outward. A positively charged electrical field would push away positive charges outward from the center. Here's the electrical field around opposite charges. The field is strongest in the middle, where the positive and negative charges combine to pull a positive to the right. Here is the electrical field around 2 positive charges. The field is 0 in between the charges because each sphere would act on a charge in the opposite direction. The field around 2 negative charges looks similar to the one around 2 positive charges, but now the arrows show that a positive charge would be drawn toward the negative charges, and the field in the middle is still 0. Here are electrical field lines around a neutral charge near a positive charge. The positive charge draws some electrons in the neutral charge to the right to create a field that has field lines pointing from the right to the left. The field lines around oppositely charged plates is uniform. This means that the field is just as strong near the plates as it is in the middle, in between the plates. Here's a little test. Do we have opposite charges here or like charges? Since there are electrical field lines in between the 2 charges, this electrical field pattern occurs between 2 opposite charges. We're going to solve this problem to find out the correct field line patterns between 2 spherical charges by first crossing out the wrong ones. Choice 1 is incorrect because the flux lines point out of the negative charge when they should be in. Choice 2 is incorrect because the field lines point into a positive when it should be out. Both charges in choice 4 are incorrect, so the answer choice must be 3. Name these charges. Since the electrical field lines point into both charges, they are negative. Notice that the field is 0 in between the 2 charges. In this presentation, you learned that physicists draw electrical field lines around spherical charges to show how a positive charge would move if placed at different locations in this field. The electrical field lines around a negative charge point towards the center to show that a positive charge would receive a force that acts in that direction. The arrows around a positive charge look similar but point away from the center of the charge, since it would push a positive charge away from its center.